그러면은 오늘 오전 첫 번째 발표할 소개해드리겠습니다. 발표하시는 토모 마츠무라 작가님이시고 카이스트에 지금 보답에 계십니다. 오늘 발표하실 주제는 shock function and weighted Grassmannian 대해서 발표해주십니다.
Oh, thank you very much. Some of you, very nice to meet you. I've been in Korea for 1 year and a half by now, and I'm having a very great time. My Korean is not so well. I can communicate, but maybe math talk. I mean, even in Japanese, I'm having a hard time explaining math, all the terms. And also, as you know, the Korean language and Japanese language is very similar. And when you switch from English to Korean or Japanese, the order of the subject, verb, objects, it's all flipped. But math is very logical language. So if you do long time math in English, then it's kind of hard to translate everything into Korean and Japanese. But anyway, so please allow me to speak in English today. What I'm going to talk about is Schur functions and weighted Grassmannians, and then it's all about Schur calculus. And Schur calculus is basically study of flag varieties geometrically, but it has so many connections to other areas like combinatorics and representation theory. Those connections are the very interesting part of the Schur calculus, and it brings people from so many different areas. Like we had a big conference in Japan last summer, and all over the world, there are so many different people came and discussed the different subjects. And I'm just doing, I think my talk, so usually flag varieties are homogeneous varieties. So it's a smooth, very nice smooth projective varieties. But I've been working on obifold, and then I was looking for sort of obifold example in the flag varieties, but I mean it doesn't exist by definition. But then the Corti and Reed started this weighted Grassmannian, just twisting the original definition a little bit, and then it gives you slightly singular spaces. And I was working with Hirakabe, who is a student in Tokyo Metropolitan University, and we managed to do whole package of Schur calculus for weighted Grassmannians. So let me just start with so there are so many flag varieties, and the very simplest example is Grassmannian, and probably Grassmannian everybody are sort of familiar with in the beginning of algebraic topology or algebraic geometry. But anyway, the Grassmannian, let's fix d and n some integers, positive integers, and this is basically the d-planes in Cn. And it's a very classical objects, and it's connected to enumerative algebraic geometry of counting the intersections of d-planes in Cn. Or this is sort of projectized version. You can think about right. I always get confused in the dimension. So counting the d-planes in Cn in the projective sense. So its original problem is actually d plus 1 planes inside of C plus n, and you try to understand how they intersect and then you projectize that problem, and you get the Grassmannian. And this intersection problem is reduced to the study of intersection cohomology of the Grassmannian. So that's the classical enumerative problem translated in the modern language. But anyway,
C is less than N. C is less than N.
Yeah, sorry. That's the classical problem. And so to build a theory, we have to have a building block of approaching to approach that classical problem, and then the key was this the Schur varieties inside of this Grassmannian. And I'm not going to give you the definition of Schur varieties, but it's just some singular, possibly singular subvariety sitting inside of Grassmannian, and it's all indexed by a partition inside of d times n minus d. So when I say partition, it's just the upside down stairs. So it's sort of indexed. So the partition of at most d rows, and that sits inside of d times n minus d. So the number of boxes in each row doesn't exceed n minus d. Okay, and so you collect all these partitions, and the Schur varieties are indexed by those things. And the key was, if you look at the cohomology of the Grassmannian, this gives you the basis. So for singular variety, it's singular variety, but it sits inside a projective variety, so it gives you a cohomology class, and it gives you a basis of the cohomology ring. And then, so the ring structure is our concern, and to determine the ring structure of this cohomology ring, you just find the structure constants with respect to, this is the cohomology class associated to the singular variety, and then you try to, if you are interested in the ring structure, you try to compute the structure constants in terms of this basis. What I mean is you expand the pairwise products in terms of the basis again. Okay, and this structure constant has the meaning, which gives you the answer to all the classical enumerative questions. But not only that, it has this number is amazingly related to so many different things. Like you can compute this structure constant in terms of certain combinatorial objects. That's the relation to combinatorics. So like examples are the well-known Yang tableaus. You count certain Yang tableaus, and then you get these numbers. And other combinatorial objects is Knudsen, Tau, and Woodward's puzzle. You solve certain puzzle and count the number of solutions to the puzzle, and that gives you these numbers. And in the relation to the representation, that's something I'm going to talk about actually today. It's the relation to Schur functions. So so this number is somehow related to representation theory of general linear group of size d. And that relation is through the symmetric polynomials. So let's look at the symmetric polynomial of parameter x1 through xd. And then inside of this, as an element of symmetric polynomials, there's some function called the Schur function, and it's indexed by a partition of at most d rows. So this is somehow the special sort of restriction of this huge partition. So this partition has to be sitting inside of d times n minus d, but I'm taking, it could be any length on the horizontal direction, but at least at most d rows. You look at any partitions inside. So this is called a Schur function, and I think I'm going to write a slightly general definition of a Schur function in a moment. So let me just say the claim. So there is a map from this ring of symmetric polynomials to the Grassmannian.
What is SD?
SD?
What do you mean?
Oh, I said this is symmetric polynomials. So this is symmetric permutations. Yeah, permutations. So the invariant part of the symmetric polynomial rings. So the relation of the Grassmannian cohomology is this surjective map from the ring of symmetric polynomials. Oh, by the way, so this Schur function actually gives you the basis of the symmetric polynomials.
Grassmannian of what? GD, GRD, and what is N in this case?
Huh? I haven't talked about.
Grassmannian, you are sending this.
Yeah. So I'm abbreviating this GR. Yeah.
This map.
Yeah.
But in this case, what is n here? You are the left hand side.
So on the left hand side, there's no n, right?
No n, right?
There's no n. On the right hand side, I have n.
So just any n, or you are sending it to n?
Yeah. So this n.
No, I'm just. This is given, but just considering only this. Okay.
So okay.
does not have
So
any-
there is a surjective map, the ring homomorphism from this Schur function that goes to the cohom. And then if lambda is inside of this, and otherwise 0.
Okay, so this is defined for any.
For any n. So somehow, right. So this Schur function are form a basis of the symmetric polynomials, and there is a ring homomorphism, surjective ring homomorphism from. It's sort of projection from the ring of symmetric polynomials to the Grassmannian. Grassmannian cohomology, the dimension is finite, but this has a dimension infinite. So it's sort of the symmetric polynomial is the universal ring which represent the cohomology of the Grassmannian. Okay, so if you want to find the structure constants in the Grassmannian cohomology, you can calculate by finding the structure constant of the ring of symmetric polynomials in terms of Schur functions. So basically, this structure constant is the structure constants of the ring of symmetric polynomials in terms of Schur functions. So that's the, right, yes, yeah. And the great advantage of having this surjective map, so this representing cohomology ring in terms of polynomial ring, is multiplying cohomology ring multiplying cohomology classes inside a cohomology ring is geometric, and it's sometimes very difficult to find how to expand it in terms of the basis. But multiplying polynomials, the actual polynomials, you can use computers and then it makes it very easy, at least in examples. And from that, computing the structure constants for the ring of polynomials, sometimes you can get a very explicit combinatorial computation of this structure constants. And that's what you have in this, the structure constants of the ring of symmetric polynomials in terms of Schur functions. It's computed in terms of this Littlewood Richardson coefficients in terms of the Young tableaus. Okay. Right, and then the side story to the relation to the representation theory is this symmetric polynomial ring is the ring of Grothendieck ring of the representation of general linear group of size D. So you can think of this as character of the representation of a GLD. So that's the relation to the representation theory, and I'm going to come back to that in a moment. All right, so this is the classical story, and then I have this weighted Grassmannian. So let me just introduce what the weighted Grassmannian is, and we just need to look at the construction of Grassmannian slightly in a particular way. So let's look at M to be n by d complex matrix, and let's say it has to be full rank, so the rank D. And if you collect all these things, there's a right action of GLD. The coefficients are all complex number, so let's maybe abbreviate C in this general linear group. And from the left, you have GLN acting. Okay, and in terms of this, the usual Grassmannian. So if you think of the subspaces spanned by column vectors, that gives you D plane inside of Cn. So, and the automorphism of this D plane is just GLD. So if you quotient by GLD of this the right action, you get the Grassmannian. That makes sense? Yeah? And then the Grassmannian flag varieties, they're very nice objects because there's nice group actions on the space. So that comes from this left action of GLN, and it's still on this Grassmannian. Still, you have GLN acting, and then this GLN it acts transitively, so it becomes a homogeneous space. So you can also write this Grassmannian as a GLN quotiented by parabolic subgroup. Okay, and of course, having the Lie group acting is good, but most of the technique we use is torus action. That's the connection to toric topology today in this talk. So there is a diagonal torus group acting on Grassmannian, so you can apply whenever you want to do some computation geometrically or compute some cohomology ring. You can use this torus action, and then you can apply a localization technique to calculate anything. Okay, and then so to get the weighted Grassmannian, I will step back a little bit, not quotienting by GLD the whole thing. We take intermediate quotient, which is quotient by SLD. Okay, so you are not quotienting by whole GLD, so there is a residual action, GLD modulo SLD, and which is, you can identify this with C star by determinant method.
Right, and the left-hand side.
Here?
No, the left line.
Here?
Yeah, what is this?
APL.
APL.
So I would have loved to say this is affine Grassmannian, but affine Grassmannian has a different meaning. So it's affine Plucker locus, APL. Okay, and still you have this. Well, let's forget GLN for now. You still have torus TN action. Okay, so so now you have TN acting on this space, and then you have C star acting on this APL. And of course, if you quotient by this C star action, you come back to the original Grassmannian. But I'm going to twist this C star a little bit so that you get something slightly different from the original Grassmannian. So let's right, so this is the definition of weighted Grassmannian. Let dW to be just C star, and then let's consider this rho W, which is the map from C star to K, which is T cross C star. And I think I should say this is complex torus. I'm not going to make a big difference between real torus and complex torus today. Okay, so you have this n plus 1 dimensional torus, and then let's.
Then is it necessary n should be even dimension?
Why?
It's n, the complex.
Huh?
GLNC is not.
Yeah, so this is GLC. I'm abbreviating C everywhere. Everything is complex. So it's a diagonal maximal torus inside a GLN.
Tn means, do you mean C star power n?
No, it's just C star, C star. It's diagonal. Diagonal matrix.
Oh, it's a complex.
Yeah, complex diagonal matrix. Right. So I'm choosing W1 through Wn, which is non-negative integers, and then U to be a positive integer. So these are the choice for the weights for the weighted Grassmannian. So this W and U are everywhere in the computation from now on. So this map, you send T to TW1, TWN, and T to DU. Okay, I'm gonna distinguish this last C star by a colon. Okay. So now the definition of the weighted Grassmannian to be a pole modulo this dW. And I could have explained this quotient as if you know Pluka embedding of the Grassmannian. So Grassmannian is the projective variety inside of the Pluka affine space given by Pluka relations. Right? The Pluka relations are homogeneous equations inside of Pluka coordinate space, and Grassmannian is defined by those relations. But you can lift this Grassmannian in the projective space to affine space, affine lifting, and then there is this weighted projective space. So that is given by those W1 through U. And so affine coordinate space, affine Pluka coordinate space, you projectize with the weights, then you get this weighted Grassmannian, if you are familiar with the Pluka coordinates. But you can also think this way. Right. So given this weighted Grassmannian, so I want to, so the symmetric polynomial subject to the cohomology of the usual Grassmannian.
If W1 to Wn are all 0.
0, then you just quotient it by C star. And then if you say U is 1, then you just quote, yes. So W1, Wn equals 0, U equals 1. That gives you the usual Grassmannian. Okay? So this is the key relation of the cohomology ring of the Grassmannian to the representation theory, which goes through the symmetric polynomials. Right? S lambda goes to the Schur classes. And then now I have weighted Grassmannian, and right now I'm gonna skip what this weighted Schur class is, but it's gonna come in a moment. So I want to find what is the polynomial ring which goes to the cohomology, which represent the cohomology ring of the weighted Grassmannian, and what are the analog of Schur function which represent weighted Schur class. So that's a very it could be naive, but it's very natural question when you have something slightly new. Okay, and then the conclusion is we found a way to. The conclusion is I can still use the ring of symmetric polynomials, and this weighted Schur function is slight twisting of the original Schur function. That's the conclusion, and hopefully I get to the conclusion in the 10 minutes. Or maybe 15 minutes. I started 5 minutes later. So. All right. Okay, thank you. All right, so I think the motivation of what I want to do is clear, and the technique or the strategy to get to this twisted version of the symmetric polynomial, the Schur polynomial, is really the equivariant geometry. So. So I think equivariant cohomology is okay for everybody, or maybe not. Right.
This is a workshop, right?
Yes. So, as I said, there's Tn action is Grassmannian, and then you can calculate the cohomology ring of Grassmannian. But as I mentioned, if you have a torus action, you can use so many different techniques to calculate cohomology ring, or so-called equivariant cohomology. And the equivariant cohomology is basically you look at universal bundle, and this is basically S infinity to the n, because this is so S1 universal bundle is S infinity, and the classifying space is CP infinity, and the cohomology of the classifying space is just the polynomial ring of one variable. Okay, So you can just take a direct products of circles for the n torus, and I can just replace this S1 by C star here. And if you replace this by C star, it's going to be just C infinity minus origin. Yeah. So the homotopically it doesn't make a big difference. So I'm not making a difference between S1 and C star. Anyway, so equivalent cohomology, you look at the direct products and then quotient by the diagonal T action on this side and this side, and then you take a cohomology. So this is a definition of the equivariant cohomology, and it's not just a cohomology. It's what's different from the original, the ordinary cohomology is it's not just a ring, but it's an algebra over the polynomial ring. So there is a natural quotient map to BT, right, on the left-hand side, the projection. So let's call this pi, and the pi star gives you the action of the polynomial ring to the equivariant cohomology. So you can think of the equivariant cohomology as an algebra about the polynomial ring, and because of that, it carries more structures and it allows us to use more different techniques, right? So now this is the equivariant cohomology of Grassmannian, and we have this equivariant cohomology of A pole. On A pole, you have K action, right? From left, you have Tn action, and from right, this is star action. And so there is a natural relation to the equivariant cohomology of. So this one is given by, you take equivariant, this space is called the Borel space, and the Borel space from A pole, Borel space of A pole and Borel space of GR has a relation. There is a natural map from A pole to goal, right? The T is a quotient of K by this right C star action, and then GR is a quotient of A pole. So there is a natural projection from here to here, and then you pull back. And the difference is this A pole is if you take a quotient by C star, the C star action on A pole is free because what? It's free, and then you get the smooth Grassmannian. So because of that, this map, if you pull back, it's an isomorphism. So let's call this F, and this is F star. It's an actually isomorphism, and then so this weighted Grassmannian, it's also quotient by dW. So there is a natural quotient map from ETW. So TW is this K modulo dW. So in the usual Grassmannian, you consider T equivalent cohomology, but for the weighted Grassmannian, there's a residual K modulo dW, TW action on weighted Grassmannian, so we can consider TW equivalent cohomology of weighted Grassmannian, and then you look at the Borel space, and there's a natural projection map from A pole to weighted Grassmannian, and this map, if you pull back, it's also isomorphism over Q coefficients. So this map is isomorphism over Z coefficients because C star action on A pole is free. But this pullback is isomorphism over Q coefficients. That's because this ZW action is not free action. It's locally free, so-called. It means that the local stabilizer is at most a finite group. So because of the finite group, that creates torsions in the equivariant cohomology. I'm skipping all these things, but because the finite stabilizer gives you a torsion in this equivariant cohomology, but all these torsions going to be disappear over Q coefficients, and that makes this pullback map isomorphism. So as a ring, as a ring, they're all isomorphic. So what's the question, right? If you want to study T equivalent cohomology of Grassmannian, you can actually study TW equivalent cohomology of weighted Grassmannian. What's the difference? I mean, they're isomorphic as rings. But when you look at this equivalent cohomology, as I said, it's an algebra over HBT. HBT, the polynomial ring. Here you have HBT action. But here you should look at TW equivalent cohomology as the algebra over BTW. So the study becomes how this polynomial and this polynomial are different. So, yeah. Right, so now I can get to, so I haven't really talked about the weighted Schur classes, but in this picture it's actually clear. So, of course, the Schur varieties inside of Grassmannian is actually T invariant subvariety. So it also gives you equivariant cohomology classes. Right? So here you have equivariant cohomology class associated to Schur variety. Right? So that is given by sort of subvariety inside of this Borel space. This way. Yeah. But let's forget about this. You have these Schur classes, equivalent Schur classes in the equivariant cohomology of Grassmannian, and then they're all isomorphic. So why don't we just pull back this class and then define it as weighted Schur classes? Yeah. So this is purely algebraically, like maybe artificial definition of weighted Schur classes. But if you are familiar with the language of stack, this is going to be orbifold, and then you should look at this as a stack. And then if you try to understand the geometric meaning of the pullback of this class by these maps, it actually gives you a cohomology, the honest equivariant cohomology class associated to weighted Schur substack inside of weighted Grassmannian. So there is a geometric interpretation of what this class is, but it just turns out that it's just a pullback of this class. So it's very natural class associated to weighted Grassmannian. Right, so that gives you weighted Schur classes, right?
Are you considering what is the definition of integral
I need this isomorphism, so from now on, everything is Q coefficients. Right. So now I'm going to spread the big picture here. You have weighted Grassmannian, the T equivalent cohomology of Grassmannian. And ordinary Grassmannian cohomology is represented by symmetric polynomials. And T equivalent cohomology of Grassmannian is actually represented by a slightly bigger polynomial ring. So you add these A parameters. So A parameter it's an infinite sequence of parameter. The index are natural numbers, so A1, A2, A2, and then to infinity. Okay, and you tensor this, and inside here you have the extended Schur function, which is called the Factorial Schur function. Right? And then if you make A equals 0, or the A parameter equals 0, it comes back to the original Schur function. So it's the equivariant generalization of Schur function. Okay? So this is a big polynomial ring, and then there is this factorial Schur function. And this also gives you the basis of this big polynomial ring as an algebra over this polynomial ring. Okay? So this is actually the direct sum over lambda of A ZA of S lambda AX. Okay? So if you make A equals 0, it just comes back to the original fact that the Schur functions are the basis of the symmetric polynomials. Okay?
If you consider A tensor or
No, it's just the indeterminants. The parameters.
Infinitely many.
Infinitely many. Yeah. So it's the polynomials.
There are infinitely many.
Infinitely many parameters. Yes. Right. So there is also this fact, symmetric polynomial represent ordinary cohomology Grassmannian, and that fact is just can be generalized to equivariant setup. This big polynomial ring represent the equivariant cohomology. There is a surjection from here to here, sending factorial Schur function to the equivariant cohomology class if lambda is sitting inside of d times n minus d rectangle, and otherwise 0. So it's a projection from this big ring. And so here you have HBT action, right? And let's just say it's a polynomial ring in y1 through yn. And here it gets a little technical. So this map is a ring homomorphism. Yeah, that's okay. But it's also an algebra homomorphism, which is equivariant with respect to this action and this action. So AL actually goes to minus y n plus 1 minus L if L is between 1 through n, and otherwise 0. So there is a projection from this polynomial ring to this polynomial ring, and with respect to that, this is an algebra homomorphism, right? So that means that if you calculate the equivariant structure constants in terms of factorial Schur polynomials of this big polynomial ring, that will give you the equivariant structure constant of this equivariant cohomology of Grassmannian. Yeah? So in that way, this big polynomial ring represents the equivariant cohomology of the Grassmannian. Okay? Okay, so I think I should relate this part.
It's always true that you have here you have projected ring algebra and then that it automatically give you, on the left hand side you have a structure constant, and then does it
because I'm sending basis to basis. So this map is defined. Yeah. So that's why the structure constants are coincide with respect to this projection from this polynomial into this polynomial. Yeah. All right. So now this is the whole point. So I use these two isomorphisms to understand what will represent TW equivariant cohomology of the weighted Grassmannian. So intermediate thing is this K equivariant cohomology of A pole. And these are all isomorphic as rings. And then here it's HBT equivariant isomorphism. And here HBTW algebra homomorphism. Because these two polynomial ring actually sits inside of this BK, HBK. Okay? So let's call this is so this polynomial ring is you have this y1 through yn, and this K has extra parameter. So y1 through yn, let's just add one more variable, which this parameter corresponds to this extra C star, which is added to Tn. Right? This y1 through yn are the parameters associated to Tn. Okay? And inside of that, there is this twisted torus polynomial ring. And let's just call this y1w, ynw. Okay? Right. So there is a surjective map from here to the TW equivariant cohomology of weighted Grassmannian. But this composition is not equivariant with respect to ZA and this Z y1w through y1 ynw. Because, yeah. But you can, so here you have this ZA action that corresponds to gy polynomial action. But here you have one more parameter, and if I can identify what this z acts on, how this z acts on this k equivalent cohomology A pole, and how can we lift this z parameter to this polynomial ring, then so you have this z a and something acting on z a x s d. So that's the what corresponds to k equivalent cohomology A pole. If I can find, so this thing corresponds to this z, and it turns out that if you take xch, which is the sum of x1 through xd, this element,
What an
x is the parameters of the symmetric polynomials. If you look at this xch, the sum of x1 through xd, this element corresponds to this z. So z sits inside of here, right? Z times 1, so that sits inside here. And that element also, you can think of it as an element here. And that element comes from this xch. So that means that I can find the subring inside of this one parameter more bigger polynomial ring, AW1, A2W. And then, so this thing also acts on this big polynomial ring.
So you choose smaller
Yes.
subring.
So this ZA doesn't help to understand the algebra structure here, but because I'm lifting this ZA polynomial to one dimension bigger polynomial ring, and inside that you can find a nice polynomial ring which corresponds to this polynomial ring. So it means that here at this level you're thinking of this tensor product, but you can also do this parameter change, and then you're just looking at the same polynomial ring but changing the parameter. And right, so from here, so once you have this picture, so now I have a map, surjective map from the same polynomial but the different parameter. There is a surjective map, and then there is a correspondence between these parameters to these parameters, and then you have nice algebra homomorphism. So from this picture, I think I'm going over too much. Once you make this AW parameter equal 0, so you have this factorial Schur function inside here, and then you apply this parameter change, and then with this new parameter AW, you make AW equal 0, and then you get a slightly different Schur function. And that will gives you the presentation of the ordinary cohomology of the weighted Grassmannian in terms of slightly twisted Schur functions. And one more advertisement is, so there is a original Schur function is the character of the irreducible representations of the general linear group. So that representation of theoretic interpretation, you can also apply what is the representation which gives you this weighted Schur function as a character. We can also calculate it, and it actually comes from the honest representation. There is honest representation. If you take the character of that, you get this polynomial. So there's also representation of theoretic nice interpretation of this weighted Schur function too. Okay, I'm sorry I'm going over too much. Thank you.
Any question or comment?
If D is wanted, the weighted Grassmannian is indeed projective weighted projective spaces. Then in this case, could you show me how to calculate the SW lambda of x?
For
For D is one case.
Hmm?
D is one case.
D is one.
Yeah.
So weighted. This.
Weight instead of weighted Grassmannian, the special case weighted projective space.
Yeah. So, as I said, Schur functions are sort of universal objects which represent cohomology of all Grassmannians. So, you don't need to specify n to write down
So,
Schur function.
I want to
Example. Yeah. Okay. I can do that. So, the partition. The simplest one is empty partition. It's empty equal 1 and both 1. Okay? And the second simplest one, and this partition is actually very important, like multiplying the Schur function with corresponding to this is called the Peary rule, and all the computation is really based on the Peary rule. So this is x1 xd. Okay, and if you twist, before I twist, I always go to factorial Schur function, right? So the factorial Schur function, the original one, is x1 xd minus a1 ad. And then now I haven't really written this AW. So ALW is AL plus WL over U XCH. Yes, I think so, yeah. So now if you do this parameter change to this polynomial, and then if you make ALW equals 0, then you get the twisted one. So maybe. So what is this? So you just put AL to be ALW minus WLU XCH. So that gives you XCH minus AWCH minus WCH over U XCH. Then if you make this equal to 0, then you get the twisted one.
Any questions? I have one question. Maybe in Schur function you mentioned the cost number and the question. C and the mu. How about the weighted Schur function case? Is there a
Yeah, it's computed. So, right. If you can calculate all these coefficients at the level of the equivalent level, then once you have the formula, you make the equivariant parameters, and then you get the ordinary structure constants. And the equivariant version, those structure constants are computed by Molev-Sagan or Knudsen-Tao. Molev-Sagan computed in terms of tableaus, and Knudsen-Tao computed in terms of their puzzle formula. And then me and my collaborator Hirakabe sort of look at their formula and use these equivalences and sort of modifying their formula, and then got the structure equivariant structure constants for this one. And that the formula is actually, it's complicated, but still written nicely in terms of Knudsen-Tao's puzzle. And theoretically, you can write down the formula also in terms of Molev-Sagan puzzle formula, Young tableau formula.
You can interpret it as a combinatorial mean.
Yes. Yeah. It's that we are not getting anything any new combinatorial objects, but when you have a combinatorial formula in the equivalent level, you weigh the combinatorial objects in certain way, and if you change this way of putting weights on each combinatorial objects, you can get the formula for the weighted version too.
Do you get positivity?
Yes, yes. So the positivity is, yeah. I haven't mentioned positivity, but in a Schur calculus, those structure constants has to be positive because you're counting combinatorial objects. That's the kind of hope everybody has. So when we calculate this structure constants for the weighted Grassmann, we also wanted to see if those structure constants become positive. And because the formula we got was very explicit, we could also prove that the structure constants are positive if the weights are non-decreasing. W1 through Wn, it has to be increasing or equal. Otherwise, you get the negative coefficient.
But then, for this case, you might have some different Schur classes or.
Well, there's always this permutation acting on the Grassmannian, so the order of the weights is not really a big problem.
No, but your choice of this
weights
class, weighted Schur classes, might not be appropriate for non-decreasing.
I don't think it has. It's very natural definition. It has to be this different. It's just that in the world of stacks, the weight matters because you're not only counting points, but if the point you calculate the intersection and you count the number of points in the intersection, but each point is OB4 points possibly, and the OB4 points are rational weighted points. So it's not whole points. Sometimes it's a 1, 2, it's a half point or 1/3 point. So that will affect the counting. That will affect counting of the points in the intersection. That makes a little complicated in the Schur calculus.
질문이 더 있으시다 하더라도 시간이 많이 됐으니까 나중에 쉬는 시간을 통해서 질문 알려주시면 좋겠고요. 다시 한번 땡큐. 다음 발표 원래 10시에 열리는데